Okay, students, today we're going to talk about 2011, number 5. And this particular problem, if you look at the overall context, this is actually a differential equation problem. Now, right now, as I'm discussing this problem, you will see the problem on the screen. But if you can have your problem right next to you as you follow along the solution, it will be most helpful. So let's read this problem together. At the beginning of 2010, a landfill contained 1,400 tons of solid waste, and the increasing function W models the total amount of solid waste stored at the landfill. Planner estimated that W will satisfy the differential equation, and it's given to us here, for the next 20 years, so it's from 0 to 20. W is measured in tons, T is measured in years from the start of 2010. So here at the start, what I would do is I look at this information. It says that in the beginning of 2010 is the start of this equation. The landfill contained 1,400 tons of waste. So what that means is that that's our initial condition. And the initial condition is that at 2010, in 2010, this is at T equal to 0, and our W is equal to 1,400. And you see, if I write this out, that gives me a sense of the initial condition. And oftentimes in the differential equation problem, initial condition comes in handy later on when we have to figure out the integration constant, right? Now let's write down the differential equation that they've given us. dW over dt is equal to 1 over 25 W minus 300. Okay? Now part A says, use the line tangent to the graph W. Now, you may ask, well, we don't know what W is. Well, that's okay. We don't really know what W is. We have the derivative of the W function. So there is a W function, W of t, which we don't really know at this point. But we do know the derivative that looks like this. Now later on we know that if we want to find this, we can simply solve this differential equation by separating the variables, integrating on both sides, figure out the integration constants, and voila, we have our W of t. But right now, just before we do that, the problem 1 didn't ask for that. Problem 1 asked for, use the line tangent to the graph W, to this unknown graph W, at t equal to 0, and we want to figure out, we want to estimate what would W be at, and this is what we want to find out. What would W be an estimated W at t equal to 1/4? You see, this is what we're looking for, estimated, and it's asking for a line tangent to the graph. Now, first of all, again, line tangent to the graph. We want that line. But how do we find that line? Every time we need to find a line, that means we need a point and we need a slope. Right? Now, a point. Well, a point is at t equal to 0. But at t equal to 0, right? So the point here is t and w, right? But at time equal to 0, what's w? 1,400. Okay? What about slope? Well, slope is derivative. And derivative in this case is dw dt. So the slope in this case is 1 over 25 at t equal to 0. Now at t equal to 0, w is 1,400. So w for this one will be 1,400 minus 300. And w, or our derivative in this case, then if you solve this out, you get 44. So our equation, our tangent line, right, follows this equation: y minus y1 equal to mx minus x1. So in this case, our problem is w minus w1, which is 1400, equal to m, slope is 44, t minus 0. So very simply, w is equal to 44t plus 1400. So at t equal to 1,4, w is equal to 44 times 1/4 plus 1400, and our answer is 1411 tons. This is the estimated value. Estimated value. 1411 tons. Okay? Now, let's go to the next problem. I'm going to go ahead and erase this. But if you didn't catch this, you may pause it, you may rewind, and try to understand this. Again, the key point here is estimation. But what method do they use for estimation? They're using a tangent line. And tangent line, again, for a line, we need a point and we need a slope, and this is the process of getting them. Okay? And then we erase part A and go to part B. Now part B says, find the second derivative, which is notated in this form, d squared w dt w. This does not mean simply squaring the derivative. This means taking the derivative again in regards in respect of t. So we can say that this is equal to so the derivative of the one. Now notice dw over dw dt is equal to 1/25 w minus 1/25 times 300, which becomes constant. So when you have 1/25 w and you take the derivative of that, you get 1/25, 1/25. But then the derivative of that will be dw, the inside function, with respect to t, will be dw dt. Okay? Very, very simple. But this is dw dt. The dw dt is written in this form, so we can say 1/25 times 1/25 times w minus 300. Okay? Because this is dw dt. Okay, so we can further simplify that. We get 1/625 w minus 300. So here we got our equation for the second derivative. Now here then, the second part of the part B says, use the second derivative to determine whether your answer in part A, remember the answer in part A was 1411 tons, using the estimate of the tangent line to figure out how many tons of waste do you have at t equal to 1/4. So here it says, we want to use this to think about whether our previous estimation was an overestimation of the true value or an underestimation of the true value. So how do we do that? Well, think about this. Earlier, imagine, let's just draw a conceptual graph, and this is not really the real graph. But say, suppose we have this graph. Pretend this is w of t. And we use a tangent line, right? we use a tangent line. In fact, actually, we use a tangent line right here. In fact, at t equals 0, to draw we use a point right here to draw a tangent line, and what we were trying to estimate was at t equal to 1/4 to see if this is what the estimation might be close to the true value. Now, with this particular graph, our estimation will be an underestimate of the true value. Why? Because the regular graph concaves up. But if we still if we think of a graph, if the graph is actually a concave down graph, where the W of t is this one, then our estimate would have been an overestimation. And the only way that can happen is that this graph concaves down. Now notice, concave up and concave down, the concavity of Wt depends on the second derivative. Concave up will have the positive second derivative. Concave down graph will have the negative of the second derivative. So what we need to figure out is whether the second derivative is positive or negative, and it will determine whether we have an overestimation or underestimation. So over here, we know that W at t equal to 0, W is equal to 1400. Now let's see what second derivative is going to be. 1 over 625 times 1400 minus 300. Well, guess what? This is certainly going to be a positive second derivative. So we can actually say, therefore, we will take this particular case. Because it's concave up, positive second derivative, so our tangent estimation will be an underestimation. Okay, so that's the rationale. Okay, let's move on. So take a moment and see the graph. Again, second part is testing your knowledge of concavity in relation to the tangent line. Let me go ahead and erase this. Now we go to part C. Now part C, to me, part C is one of those freebie questions. Why do I say freebie questions? It's a very straightforward solving the problem question. And in fact, this one actually consists of 5 out of 9 points. So it's probably going to be the 5 easiest points that you can get from this exam. Part C says find a particular solution of this differential equation. Now we know that solving the differential equation means we are solving for W of t. And in order to solve that is that we need to be able to separate variables, integrate both sides, and so on and so forth. So let's go through this process. So dW over dt is equal to 1 over 25W minus 300. So I'm going to go ahead and separate variables. So I will say dW is over W minus 300 is equal to 1 over 25 dt. This is separation of variables. Separation of variables. Then what we do next is we integrate on both sides. Obviously, we've done this so many times in our course that we now know straightforwardly. We know that this is ln W minus 300, and this is 1 over 25 t plus c1. Now we say c1 is because we know that the other c is going to come up. Then we e on both sides, and we end up with W minus 300 equal to, now notice that this is e to the 1 over 25t times e to the c1. Right? The addition of the exponent makes it a multiplication of the base to the first exponent times the base of the second exponent. Now e to the c1 is just another c, So I'm going to go ahead and call it C2. C2 times e to the 1 over 25t. If you had trouble with this process, go back to your notes from chapter 7, I believe, when we went over the differential equation. So now we have a very simple problem. W is equal to C2 e to the 1 over 25t plus 300. This is our general equation. We want to find a particular equation at t equal to 0 when W is equal to 1400. So that's very simple. We can just take this and put it in here. W is 1400. C2 is just C2. E to the 1 over 25. T is equal to 0 plus 300. Okay, bring the solution over here. Then what we have here is 1100. Right, bring the 300 over there. Becomes 1100. 1400 minus 300. 1100 is equal to C2 times e to the 0. E to the 0 is 1. So C2 is 1100. So therefore, this is what we have. W is equal to, I'm using this general equation and replace 1100 with C2. So 1100 e to the 1 over 25t plus 300. And here you have it. Here is your particular equation. And we can say the domain for t is from 0 is less than t, less than equal to t, less than equal to 20. Why? Because we're talking about for 20 years. And this is our answer. You see, this is probably the 5 easiest points you can get on this entire section in 2011.